What if I told you that the biggest AI labs in the world are hiding their most crucial secret in plain sight, and a single lone researcher just figured out a mathematical way to crack it wide open? If you've been paying attention to the AI space at all, you know that the true capabilities and sizes of these models completely dictate the future of tech, coding, and honestly, our daily lives. But how can we measure what we aren't allowed to see? That is the multi-billion-dollar question, isn't it? How big is ChatGPT really? The top frontier labs, places like OpenAI, Google, Anthropic, they absolutely refuse to tell us how massive their proprietary models actually are. They treat parameter counts like highly classified state secrets, which leaves the rest of us totally in the dark, basically trying to guess the size of the engine while the hood is welded shut. Now, the old way of guessing how big these models are was mostly based on inference economics. Analysts would look at API pricing, token throughput, or GPU hardware costs to estimate the size. But there's a massive catch. This method carries a 2x or greater uncertainty. It is incredibly flawed because it relies on all these external factors like server stacks and quantization.
So one researcher tried something different, a mathematical way to probe these black boxes, simply by giving them a highly specialized trivia test. It's a clever idea. Whether the specific numbers it produces hold up is a different question, and we'll get to that.
Let's move into Section 1, the AI black box.
And look at how this method actually works. It's called the densing law.
We have all seen the headlines, right? A tiny 7 billion parameter model from this year completely matching a massive 70 billion parameter model from last year on reasoning tests or math benchmarks. Because of this, people mistakenly assume that AI scaling is just dead. They think, hey, we don't need bigger models, we just need smarter, denser, small ones. But that entirely misses what's actually happening under the hood. The crucial point here is that we have to separate two totally different types of AI brainpower. Think of it like a 5-year-old learning. First, we have compressible procedural capability. That's learning a rule, like addition or basic logic. Once you learn the rule, you compress that knowledge and apply it to a million different math problems without needing more physical brain space. But then we have incompressible factual capacity. This is random, obscure trivia. We're talking about the specific founding year of a random bridge in Europe or the exact name of a specific computer science paper. You cannot logic your way into knowing that. You either memorized it or you didn't. And memorizing it requires dedicated physical memory space inside the model's parameters. Enter the breakthrough hero of our whole explainer, Incompressible Knowledge Probes, or IKPs. This is a rigorous benchmark of 1,400 highly obscure factual questions designed to isolate pure, incompressible memory capacity. It essentially filters out anything an AI could possibly guess or reason out. The thesis is brilliant in its simplicity. Because storing facts requires physical space in a neural network, measuring exactly how many obscure facts a model has memorized gives you a hard mathematical lower bound on exactly how many parameters it must have. Section 2, Decoding the Mystery. Let's break down how these IQPs actually work in practice. So how do you build a test that a super smart AI can't cheat on? First, the researchers gathered facts from Wikidata and obscure academic citations. Then they rigorously filtered out anything guessable, like alphabetical rules or obvious name associations. Finally, they organized all of this into 7 distinct tiers of obscurity. This isolates knowledge bounded by a concept in information theory called Shannon Entropy. Basically, think of it like trying to pack a suitcase. Shannon Entropy proves there is a physical limit to how tightly you can fold your clothes. You literally can't compress a random fact into zero space. It requires a minimum number of bits to store.
By walking a model through these tiers, you can find roughly where it runs out of memorized knowledge.
Tier 1 is universal knowledge, like asking for the capital of Norway. Super easy. Tier 4 gets into obscure attributes, maybe the founding year of a minor unknown university. But Tier 7 is borderline impossible rare facts. It's like asking the AI to name a very specific, low-citation computer science researcher's unique artifact. By finding the exact tier where a model starts hallucinating or failing, we can map its literal capacity. And the results here are just brilliant. The researchers took this test and ran it on 89 open-weight models, where we actually do know the exact parameter counts, models like Llama and Quen. Across all 89 models, ranging from 135 million all the way to 1.6 trillion parameters, the knowledge scales in a perfect log-linear trend line.
This part of the paper is on firm ground. On known open-weight models, IKP scores actually do predict parameter count with real precision. It's also what lets the researchers push back on the densing law myth we talked about earlier.
When you plot factual memory over time from 2023 to 2026
at a fixed parameter count,
it is a perfectly flat trend line. It proves that factual memory absolutely does not compress over time.
The way procedural skill does.
Smaller, recent models know no more incompressible facts than older models of the exact same size. Procedural reasoning gets denser, sure, but facts will always demand physical space. Section 3, the big reveal. Let's get into the real-world implications of all this. Okay, here is where it gets incredibly exciting. We now have a perfect mathematical ruler.
And now here's where you need to slow down, because this is the part that actually matters most. Once you've calibrated this ruler on models where you already know the true size, the obvious next move is to point it at the closed source, proprietary giants that won't tell us their size. And the paper does exactly that. GPT 5.5 comes out at an estimated 9.7 trillion parameters, Claude Opus 4.6 at 5.3 trillion, Gemini 2.5 Pro at roughly 1.2 trillion. Those are the headline numbers everyone's going to quote from this paper. Here's the problem. Within days of this going up on arXiv, other researchers reproduced the author's own code and found the closed model estimates don't hold up. A flooring bug in how small models were scored inflated their apparent performance, which throws off the whole calibration curve at the high end. The author himself responded and admitted that depending on which reasonable hyperparameters you pick, GPT 5.5's estimate swings anywhere from 1.9 trillion to 10.4 trillion. That's not a small margin of error. That's the entire estimate being up for grabs. He said outright that he should have reported a range instead of a single number, and that he published knowing the closed model piece was premature. So take the trillion parameter figures with a serious grain of salt. What doesn't fall apart under scrutiny is the underlying structural finding about mixture of experts models. In an MOE model, only a small fraction of the parameters are active at any one time, which saves compute. But the data shows it's the total parameter count, not the active fraction, that predicts how many facts a model knows. The dormant experts still hold memorized knowledge. That relationship held up cleanly across the open weight models where ground truth is known, and it's a genuinely useful structural insight, regardless of what happens to the specific closed model point estimates. There's also a real behavioral finding buried in here. Claude Sonnet 4 scores noticeably lower on this test than the older Claude 3.7 Sonnet, and it's not because the model got smaller or dumber. Its refusal rate on these probes jumped from % to 88% between versions. The model isn't forgetting facts, it's declining to answer them, which is a very different thing and worth separating from the raw capacity question this whole paper is about. Section 4, the T7 cliff. Let's look at the one part of this that's hardest to argue with. Regardless of what the exact trillion parameter figures end up being, Tier 7, the hardest tier in the whole benchmark, breaks nearly every model that takes it. The paper reports every major frontier model it tested scoring at or near 0% on Tier 7. That part doesn't depend on the disputed calibration curve. It's a direct measurement, and it says something real about where current models simply run out of memorized coverage. Standard benchmarks like NMLU or the medical exams are maxing out, but that saturation isn't evidence that scaling has ended. It might just mean those tests stop measuring the deep, long tail of human knowledge that's still out there, waiting to be absorbed by something bigger. So here's what I'd actually take from this paper. The method is clever, the open weight calibration is solid, and the MOE finding and the Tier 7 cliff both hold up. The specific multi-trillion figures for GPT 5.5, Claude, and Gemini are the least reliable part of the paper by the author's own admission, which raises the real question worth sitting with. If even the person who built the ruler doesn't trust the specific numbers it produced on closed models, how many other "we finally measured it" AI claims are one hyperparameter away from falling apart?